get the balls on this motherfucker. Stay low, stay low. With so much drama in the LBC, it's kinda hard being Snoop D, no double G, but I somehow, some way, keep coming up with funky ass shit like every single day. May I kick a little something for the cheese and make a few ends as I breeze through. 2 in the morning and the party still jumping 'cause mama ain't home. I got bitches in the living room getting it on and they ain't leave till 6 in the morning. So what you gonna do? Shit, I got a pocket full of rubbers and my homeboys do too. So turn off the lights and close the door. But for what? We don't know how. Yeah. So we gon' smoke an ounce to that. G's up, hoes down, while you motherfuckers bounce to that.
Number of attempts does not matter.
Laid back. With my mind on my money and my money and my mind. Rolling down the street, talking laid back. With my mind on my money and my money. Back. I got me some secret gin. Everybody got their cups, but they ain't chipped in. Now this type of shit happens all the time. You gotta get yours before I gotta get mine. Everything is fine when you listen to the D.O.G. I got the cultivating music that be captivating me. Who listens to the words that I speak as I take me a way to the middle of the street and get to like to this bitch named Shady. She used to be the homeboy's lady. 80 degrees when I tell that bitch please raise up all these NUTs cause you get none of these at ease. As I mob with the dog town filled with breeze, the I chuck jet. Rolling down the street, talking laid back. With my mind on my money and my money on my mind. Rolling down the street, talking laid back. With my mind on my money and my money on my mind. Later on that day, my homie Dr. Dre came through with a gang of tangled rap and a fat ass Jake of some bubonic chronic that made me choke. Shit, this ain't no joke. I had to back up off of it and sit my cup down. Tangled Ray and chronic, yeah, I'm fucked up now, but it ain't no stopping. I'm still popping. Dre got some bitches from the city of Compton to serve me, not with a cherry on top. Cause when I bust my nut, I'm raising the vodka cop. Don't get upset, girl, that's just how it goes. I don't love you hoes, I'm out the door, and I'll be rolling down the street, talking sipping on good laid back. With my mind on my money and my money on my mind. Rolling down the street, talking sipping on good laid back. With my mind on my money and my money on my mind. Rolling down the street, talking sipping on good with my mind on my money and my money on my mind. Rolling down the street, talking sipping on good with my mind on my money and my money on my mind.
All right. And it wants to know the probability of making a hole in. So if the probability of making a hole in one is 1 out of 2479, what is the probability that all 4 golfers make a hole in one? Draw a tree. Tree is the way to go here, right? First golfer. Does the first golfer make a hole in one, or does he not? Makes a hole in one with probability 1 over 2479. And of course, I mean, for completeness, if you want, 2478 over 2479 for the knot. And continue on. Second golfer. Does he or she make a hole in one or not? with probability 1 over 2479 again, or 2478. And so on and so on. Exactly. For questions with at least, what is the best way to solve? Who knows? You have to adapt. And we're going to do an example of that right now in number 18. Number 18 tells us that we have a club with 9 male and 11 female members. We are asking the question, how many committees can be selected that have how many 5-member committees? Sorry, how many 5-member committees? Committees with at least 4 women and B, no more than 2 men. Does the ninth hole part impact the question at all? It does not. It does not, right? All right, so 2 separate questions, right? You realize that? We have a club with 9 male and 11 female members. How many 5-member committees can be made with at least 4 women? And that goes back to Javier's question. What is the best way to solve at least questions? Well, again, you want to adapt. What does it mean to have at least 4 women? So at least 4 means 4 or 5 in this case, right? I mean, it's a 5-person committee. So either you're going to have 4 women or you're going to have 5. And that's very manageable. That's very manageable. So the best way to deal with this is to evaluate exactly that. The 4 women, the number of 4 women committees, and the number of 5 women committees. So here's my question to you. How many groups of 4 women can you have? Right? How many ways can you choose 4 women? How many 4 women committees can you have? Well, you have 11 female members. So you want to choose 4 out of those 11. 11 choose 4. Exactly that. Right? Here you're going to have, this is the number of 4 women committees. Now you want a 5-member committee. So you're going to need 1 man. Now imagine all of these committees. These are all the possible 4 women committees. And then throw in 1 guy into each committee. So 1 guy goes around, and then you have these 5-person committees with 4 women, 1 guy, but now you're allowed to vary that male, right? How many ways can you vary him? Now you choose 1. Exactly that. Right? So this is the number of 4 women committees. You're going to choose 4 women from the 11 and then choose one of the 9 male members. So that's the 4 women committees. Now let's do the 5 women committees. Well, you want to choose 5 of the 11 women and none of the male. This is, of course, not really necessary, but if you want to draw a parallel, it's a nice thing to point out. This will, of course, be 1, but there it is. This is the number of committees, of 5-member committees with at least 4 women. No more than 2 men? What does that mean? That means either 0 men, 1 man, or 2 men. Exactly that. And here's the 0 men. Here's the 1 man. So we already have 2/3 of the work done. So 11 choose 5, 9 choose 0, that's 0 men. 11 choose 4, 9 choose 1 is the 1 man. And now you are left with the 2 men committees. In other words, 3 women, 2 men. 3 women, 2 men. Exactly that. How are we doing here? Right? You've practiced this. You know what's going on. We want to do a few more. Welcome back, Wayne. 24. In how many ways can 5 out of 9 plants be arranged in a row on a windowsill? In how many ways can 5 out of 9 plants be arranged in a row on a windowsill? You tell me. What's going on here? Right? This is the number of permutations of 9 elements taken 5 at a time. Because the order matters. Exactly. Right? Even if the plants do look alike, you can tell which one is which. And if you change them around, I mean, it's almost impossible to have 2 identical looking plants, there's always a little difference. So permutations, the order does matter here. "34, Baskin-Robbins advertises that it has 31 flavors of ice cream. How many different double scoop cones can be made? Assume that the order of the scoop matters." How many double scoop cones? I mean, they tell us that the order matters. Of course, you know that the order matters. The order might not have mattered to you, but to your 5-year-old nephew or niece, the order matters very much. So we have a double scoop cone. Of course, the scoops are one on top of each other, right? Because if they were side by side, it's a whole other story. How many double scoop cones, you tell me? I don't know about that. How many choices for the one on the bottom? Well, we've got 31 choices for that one. And then how many choices for the one on top? 31 as well. Isn't it 31 squared? In the 31 choose 2, you're making the assumption that the ice creams have to be different. They don't. Nowhere does it say that the ice creams have to be different. 31 squared. Follow-up question: how many triple scoop cones can be made? Well, now that's easy, right? point, Britain? The question does say different double scoop cones, but I think it refers to the cones that are different and not the flavor that is different. As Hannibal suggests, nobody is going to prevent you from taking the same ice cream twice. Now you understand the issue here, right? I mean, suppose you have your cone. You've seen these. I'm going to stop drawing now because it looks like I could be drawing something else. You know these cones, these side-by-side ice cream cones there, where the order doesn't matter. How many double scoop cones if the order does not matter? Right? The 31 choose 2. But in here, what's happening? You're choosing 2 flavors from 31. Right? You're choosing 2 flavors from 31. This is without replacement. Right? Like you're being dealt 2 cards from a stack of 31. So you're missing stuff here. What are you missing? Plus 31. Thank you, Annie. You're missing still the same double scoops, right? The double chocolate, the double vanilla, the double swirl, and whatever. You've got 31 of those because you've got the 31 flavors. Well, in here, 31 choose 2, you're choosing 2 flavors from the available 31. Here, this is without replacement, right? It's like choosing 2 cards from a deck of 31 cards. You're being dealt 2 cards. You're never going to have the same card twice. Could be 2 aces, but it's never going to be 2 aces of hearts. Right, so here, this is the number of different ice cream double scoops where the order does not matter. And you still have the opportunity to take both scoops the same. 31 of those cones. So, and choose R assumes no replacement, absolutely. Absolutely. It's the number of combinations of n elements taken R at a time. So you have those n possibilities and you take R of them. Right? I mean, it's like, again, you think Lotto 649 combinations. Lotto 649 chooses 6 numbers, but once one number has been chosen, you can't choose it again. You've got those balls in a bowl there, 49 balls, and you're choosing 6 numbered balls. So you cannot choose the same number twice. You're not choosing the same flavor twice. How many triple scoop cones? If the order does not matter. So 31, choose 3. This is the number of cones where all the flavors are different. Right? Where all the flavors are different. And Annie is suggesting 31, choose 2, where you're only going to choose 2 flavors. One of them is going to be double. Very nice. Very nice. Very nice observation. And then 31, choose 1, where all the same flavors, all the 3 scoops are the same flavor. So this is the nice way to see it and extend the idea, right? This 31, this plus 31 here could have been viewed as 31, choose 1. Very nice. All right, let's move on. Let's move on with the, so here, this is the number of cones where all the ice cream is different. Right? This is the number of cones where all the flavors are different. Now, I mean, what can happen, right? I mean, you've got these 3 scoops. Either they're all different, or 2 of them are the same and 1 is different, or they're all the same. These are the 3 possibilities. If they're all the same, it means you're just picking 1 flavor. So picking 1 flavor out of the 31 flavors. If 2 of the scoops are the same and 1 is different, it really means you're picking 2 flavors. You're picking 2 flavors out of 31. So really the question is, how many flavors are you picking? You're either picking 3 flavors or 2 or 1. That's the argument. What we want to do now is bring all of this all of these counting arguments to a probability setting. Right? We've been counting. Now let's throw in some probability into the mix. So consider the following scenario. A basket contains 7 red and 4 yellow apples. Number 2, find the probability that a sample of 3 apples is drawn. Find the probability that the sample contains all yellow apples. Is everybody with us here? Right, you've understood the problem. You have a basket containing 7 red and 4 yellow apples. A sample of 3 apples is drawn at random. What is the probability that all the apples are yellow? Several approaches. One easy way is using trees. Trees are very useful here. Let's set up a scenario using trees. You're drawing 3 apples at random. What's the first apple going to be? Well, it's either going to be yellow or red. You're choosing these at random. So what is the probability of picking a yellow apple? Well, you've got 4 yellow apples out of 11. Probability, 4 out of 11. Probability of choosing a red apple, 7 out of 11. Right? I mean, we're just doing this second branch for completeness. Of course, it's not going to help us here, but it's nice to have it nonetheless. You're going to draw a second apple. Again, it's either going to be yellow or red. But that's going to depend on what happened first, right? I mean, you already chose a yellow apple. So now your basket only contains 10 apples, 3 of which are yellow. So the probability of choosing another yellow apple, 3 out of 10. You still have 7 red apples in the basket. So the probability of choosing a red apple is 7 out of 10. Again, the branches have to add to 1. If the first apple you picked was red, you still have 4 yellow apples in your basket of 10 apples. 4 out of 10 is the probability of choosing a yellow apple if the first one was red. If the first one was red, you only have 6 red apples left in a basket of 10. Probability of choosing red, 6 out of 10. Again, notice how these add to 1. Your third apple what's the third apple going to be? It's either going to be yellow or red. Of course, you didn't need to draw the whole tree, right? You understand that the only thing you're interested in is all yellow apples. So yellow for the first, yellow for the second, yellow for the third. That's all we're interested in. We completed it as a nice exercise, but it wasn't necessary for us. If your first pick was a yellow apple, your second pick was a yellow apple, there are only 2 yellow apples left in a basket of 9 apples. 2 over 9. Still 7 apples left, 7 red apples, so a probability of 7 over 9 of choosing a red. Thank you, Annie. If the first apple chosen was yellow and the second apple chosen was red, you have 3 yellow apples left and 6 red apples. 3 out of 9 versus 6 out of 9. If the first apple chosen was red and the second was yellow, again, you have 3 yellow apples left and 6 red apples left in a basket of 9. And finally, if the first two chosen apples were red, you have 5 red apples left and 4 yellow apples left. 4 out of 9 versus 5 out of 9. Probability of choosing all yellow apples is this single branch. 4 out of 11 times 3 out of 10 times 2 out of 9. There it is. 24 over 990. I guess I could have simplified that. That's a 5, that's a 3. 15, 150, 165, 4 out of 6. Thank you, Thomas. There you go. Hopefully this tree will be useful for the second question. Seems like a waste to do just one question. More red than yellow apples. What is the probability of choosing more red than yellow apples? What does more red than yellow apple mean? It means 3 red or 2 red apples, right? Because you have a sample of 3 apples. So it's 2 red, 1 yellow, or 3 red. Thank you, Annie. So luckily we still have our tree diagram here that will be useful. And what do these things mean? Well, the 3 red is right here. That's this last branch. And let's pick out the branches where you have 2 red and 1 yellow. So red, red, yellow. It's 2 red, 1 yellow. Red, yellow, red. That's 2 red, 1 yellow. And red, red, yellow. So 1, 2, 3, 4. These 4 branches. So let's add these up. 3 red. That was 7 over 11 times 6 over 10 times 5 over 9. And then 2 red and 1 yellow. Those are the 3 other branches. 4 out of 11, 7 over 10, and 6 over 9. 7 over 11, 4 over 10, not plus, but times, 4 over 10, and 6 over 9. And finally, 7 over 11. Oh, have I made a mistake here? I have made a mistake. What was I looking at? Jeez. 7 over 11, 4 out of 10, 6. Okay, we're good. 6 out of 10. And finally, 4 over 9. There it is. Sorry about that. Got lost in the branches there. Everybody with us? How are you doing? Let's redo this without using trees. Should the 6 over 9 for the first, should be 6 over 9 for the first one. This one here. This is all 3 red. Right, so it's this last branch here. Let's call this branch 1. So 7 over 11 times 6 over 10 times 5 over 9. Let's convince ourselves a different way. It's all good. Yeah, no, I don't want to convince ourselves a different way here. What I was going to say is you could have made a sample space of equally likely outcomes, even though the probabilities seem very different here. There's still a way to make a sample space of equally likely outcomes, right? You have a basket. Yep, Mark is asking if we have a choice to choose whichever method we want to use during an exam. You have complete freedom to do as you wish. Unless, of course, the question is specifically asking you to do something. Right, like solve using the simplex method or that kind of thing. I mean, in the case of a probability, I mean, like, question could force you to use something, but in most cases, you'll have complete freedom. What I was going to suggest is you could imagine your barrel of apples. Right? You have 7 red apples, so you could call them R1, R2, all the way to R7, and 4 yellow apples, Y1, Y2, Y3, and Y4. And now you could make a sample space of equally likely outcomes if you have a sample of 3 apples. So your sample space could be R1, R2, R3, or R1, R2, R4, and so on, all the way to R1, R2, R7, and then R1, R2, Y1, and so on, and do all of the possible combinations. You could have done a choosing argument as well. Absolutely right. Right? How could we have done some sort of choosing argument? So many options, right? I mean, first of all, this sample space of equally likely outcomes doesn't seem very manageable here. So let's not do that. But if we're looking at a counting argument, right, instead of trees, if we do a counting argument, what do we want to do here? We want to choose 3 red apples. How can we do that? Well, that's 7 choose 3. We want to choose 3 red apples from the 7. And if you want 0 from the yellow. And in how many ways can you choose 2 red and 1 yellow? Now you want to choose 2 red from the 7 red and 1 apple from the 4 yellow. So that's the total number of ways that you can choose either 3 red or 2 red. Now, how many possible 3 apple samples can be drawn? Well, you have a total of 11 apples, and you want to choose 3 of those. 11 choose 3. 11 choose 3 is the total number of 3-person committees that you can make from 9, or 3 apple samples you can make from 11. And, you can convince yourselves that this is exactly the same thing. So do it this way, do it that way, see what happens. Before I erase this, let's revisit the first answer we had, right? Probability of all yellow. We had worked it out as 4 over 11 times 3 over 10 times 2 over 9 using trees. Let's redo the argument using a counting argument, very much like this, right? What do we want to do? We want to choose the 3 yellow from the 4 yellow. So in other words, 3 of the yellows, 0 of the reds, over all possible ways to choose 3 apples. 11 choose 3. Right? Let's see. Let's see this in action. This is by definition 4 factorial over 3 factorial times 1 factorial. This is 7 factorial over 0 factorial times 7 factorial. And this is 11 factorial over 3 factorial times 8 factorial. This is, of course, just 1. This is 4. And here, 11 factorial over 8 factorial. You're missing 9, 10, 11. 9 times 10 times 11 over 2 times 3. Or 2 times 3 times 4 over 9 times 10 times 11. 2 times 3 times 4 over 9 times 10 times 11. Very nice. Right, so a very nice approach either way. In a club with 9 male and 11 female members. A 5-person committee is chosen. What is the probability that the committee contains what is the probability that the committee contains 2 men and 3 women? We did a question very similar to this before, right? Let's count how many committees can be made with 2 men and 3 women, and we'll divide by the total number of committees that can be made, right? So imagine a sample space of equally likely outcomes here without actually writing it down. How many committees can be made with 2 men and 3 women? What do we want to do? We want to choose 2 men out of those 9. 9 choose 2. And we want to choose 3 of the 11 women. So this is the total number of committees consisting of 2 men and 3 women. How many committees in total? Right, we have 20 people altogether. We want to make a 5-person committee. 20, choose 5. There it is. Probability of no more than 2 men. Right, so what does that mean? No more than 2 men. It either means 0 men, or 1 man, or 2 men. I mean, we've noticed that before, right? So probability of 0 men plus probability of 1 man plus probability of 2 men. But the 2 men, 3 women, we have it right there, right? So what's the probability of 0 men? You want to choose 0 from the 9. So 9 choose 0. In other words, all of them from the women over the total number of 5 people committed. And 1 man, so 9 choose 1. 11 choose 4. And finally, 2 men, or 2 men and 3 women, we have it right there. 9 choose 2. 11 choose 3 over 20. Choose 5. Questions? How are we doing here? Too easy? Find the probability that the 2-card hand described above, wait, where's it above? 2 cards are drawn at random from an ordinary deck of 52 cards. Find the probability that the 2-card hand contains, so probability that a 2-card hand contains two aces. You know what's going on, right? You've seen Texas Hold'em played on TV if you're not playing it yourself. What's the probability that you're going to pick up 2 aces? Right? I mean, Texas Hold'em, everybody's dealt 2 cards. What's the probability that you pick up 2 aces? Well, there are only 4 aces in the deck. So the probability that you have 2 aces, you want to have 2 of those 4 aces. So that's how many 2-ace hands you can have. And how many total hands? It's 52, choose 2. How many card hands from a deck of 52? Thank you, Annie. There it is. I think it's worthwhile to work that out here. It's 4 factorial over 2 factorial, 2 factorial, 52 factorial over 2 factorial, 50 factorial. We can cancel one of those 2 factorials there. This is 3 times 4 over 51 times 52. So about, well, Britain has the exact number, 1 out of 221. I mean, it's not terrible. It's not a terrible probability, right? I mean, if you play enough hands, eventually you pick up a pair of aces. Probably. Right? You would expect 1 out of 221 hands. Can we do it via tree method? Absolutely. Absolutely. Let's do via tree method. What's your first card? Well, it's either an ace or it's not. What's the probability that it's an ace? You have 4 aces out of the whole deck, out of 52 cards, so 4 out of 52. Probability that it's not, 48. Right? You have 48 cards that are not aces. Once you have your first card, what's your second? Well, I mean, either it's an ace or it's not. And as somebody came to my office hours yesterday, I mean, since we're not in this situation, it makes sense to stop it right there, but it looks nicer to have a branch and I mean, if you didn't pick up an ace in the first card, it doesn't matter what you get. Whatever you get with probability 1, you're not going to be in that situation anyways. Right? If you picked up an ace in the first card, how many aces are left? You've got 3 aces left, and you've got 51 cards in the deck left. So you have a 3 out of 51 chance of getting another ace. If the first one was an ace, then you still have 48 cards that are not aces out of 51. Again, notice how the branches add to 1. Here you've just got the 1 branch. It's 1. John is asking if on an exam we can go straight to this. You can go straight to that. You should maybe say, I want to choose 2 aces out of 4, divided by maybe a slight justification as to why it's 4 choose 2. But yeah. So what do we want? We want this branch here, ace ace, 4 out of 52 times 3 out of 51, exactly the same thing. Very nice. So everything's coming together nicely, wouldn't you say? Let's follow that up with the probability of all spades. Can all of these questions be done using trees? Short answer, yes. Long answer, maybe your tree is very long. And so you probably don't want to do that, right? I mean, this is just a 2-card hand. So this is all good. But what if you have a 5-card hand, right? What if it's regular poker? Do you really want to write out all the possibilities? Right? What if the question is, what's the probability of having a flush straight up? Right? What's the probability of being dealt a flush in regular poker? You probably don't want to do a tree diagram. Consider this, probability of all spades. What do we want? We want We want to choose 2 spades out of the 13 spades. Divided by all the possible hands. Again, let's work that out because it's important to understand where we're going with this. 11 factorial over 52 factorial, 2 factorial, 50 factorial. Again, these cancel out nicely. And we get 12 times 13 over 51 times 52. Very well. And what do I want to point out here? What is the probability of suited cards? Right? What is the probability of having 2 cards of the same suit? 2 hearts, or 2 diamonds, or 2 spades, or 2 clubs? Well, of course, all spades, or all clubs, or all hearts, all diamonds, it's the same probability. Right? So the probability of having suited cards is just going to be 4 times this probability, right? You could either have 2 hearts, or 2 spades, 2 diamonds, or 2 clubs. So that plus that plus that. In other words, 4 times this. And 4 times 13 is 52. So these cancel out nicely, and we get 12 out of 51. Which is about 1 in 4. Right? Say, so 1 out of 4 times you're going to get suited cards. That's why sometimes you're misled if you're playing Texas Hold'em and you're thinking to yourself, I've got suited cards, I want to go in, but 1 out of 4 times you're going to get that. So that's garbage. Yeah, but it's yes, flush opportunity, but you see that it's not unusual to get suited cards. So that's why, I'm sure if you're familiar, the saying goes, suited connectors, high cards, you want 2 out of 3. But, so somebody's suggesting you don't have to calculate odds of 5 spades out of 7 cards for poker, but that's what's happening if you're playing Texas Hold'em, right? You've got 2 cards and 5 community cards. So, yeah. Why don't we follow that up with the probability of only face cards? and face cards and or ace. Right. In other words, high cards, jack, queen, king, or ace. I mean, I'm sure they did not include ace in that probability, but let's do it because these are the high cards. So what do we want? We want two of these cards to come from jack, queen, king, or ace. In other words, 2 out of those 16 cards. And you're dividing by, again, the total number of 2 card hands. 52 choose 2. What is that? It's going to be 15 times 16 over 51 times 52. Again, no, not again. Wait, is it? Yeah, probably again, kind of close to 1 over 4. All right. Yeah, maybe not that high. All right, how are we doing here? Questions? We have time for a few more. Where are we? Consider this, buddy. 26. Yeah, we didn't. We're actually not getting to the birthday question yet. Is it due on the 3rd? I'll postpone it. I'll postpone it till Thursday. Consider this. We'll end with this question here. 26 slips of paper are each marked with a different letter of the alphabet and placed in a basket. A slip is pulled out, its letter recorded in the order in which the slip was drawn, and the slip is replaced. This is done 5 times. Find the probability that the following words are formed. Somebody remind me to postpone the web work, though. I might forget. Because right after class, I have to run and do an errand. So then it might, so somebody email me. What are we doing? We have the 26 letters of the alphabet written on slips of paper, choosing a slip at random, recording the letter. Thank you, Lance and Ann. We'll record the letter and put the slip back. We're doing this 5 times. So you're going to get a string of 5 letters, a 5-letter word, if you will, what's the probability that the word starts with P? How can you get a letter starting with P? The first slip better be a P. You only have one P out of 26 letters. 1 out of 26. That's it. What's the probability that the word contains no X, Y, or Z? Well, you want to make a 5-letter word. Let's count. First of all, how many 5-letter words are there? If you are choosing a slip at random, recording the letter, putting it back, choosing another one, how many possible 5-letter words? "26 of the 5 possible 5-letter words." This is going to be our denominator. This is all the possibilities. We want to make a word that does not contain X, Y, or Z. How many choices for the first letter? For sure, it cannot be X, Y, or Z. So we have 23 choices left. Once you've had one of these choices, how many choices for the second letter? Still 23. And for the third, still 23, and so on. 23 to the 5 possible words without X, Y, Z. So the probability is this. How are we doing here? Questions? Anybody? I've released the last of the web work assignments, right? And at least one of Lance and Anne will email me so that I don't forget to postpone the second to last one. So I'll give you an extra few days. And we'll pick this up again next week. Why is it to the power of 5, right? I mean, it's a 5-letter word. I mean, while it doesn't say here, it was a 5-letter word. WebWork 7 is not released. I'm going to look into that. I suspect, yeah, I believe I've released a WebWork 6. Is that correct? Yeah, WebWork 6 will be the last one. Yeah. All right. Thank you all for coming, folks. Good. You guys have a good Easter break, and I will see you next week. You guys have a good one.